Hey guys, Mr. Backerberg here. In this video, we're going to take a look at exponential decay. When we're talking about exponential growth versus exponential decay, the equations are going to look very, very similar to each other. It's going to be something that looks like y equals k times a to the x, and k is going to be some number that's bigger than 0. The biggest difference in growth versus decay is what that a value looks like. If your a value is any number bigger than 1, then your equation is going to represent an exponential growth model. But if your a value, if your base is some number between 0 and 1, some fraction or some decimal number, then that's going to be exponential decay. Exponential growth is where we get that nice J curve for our graph, where it keeps extending up forever and ever and ever without bound. And exponential decay is more of that L curve, where we keep gradually approaching 0 as we go further and further out to the right. When we're dealing with an equation in this form, that k value typically represents your initial amount. Especially when we're talking about real-life models, that's your starting amount of whatever it is that you're dealing with. And then your a value base is your growth or decay factor, depending on if it's bigger than 1 or if it's some fraction or decimal number. So taking a look at this example, we're going to model some radioactive decay. So we're going to use that equation y equals k times a raised to the xth power. So we know that the half-life of a certain radioactive substance is 20 days. And there are 5 grams present initially, and we want to figure out how long it's going to take for there to be only 1 gram remaining. Now, as we're writing out this decay model, most of the information follows what we were just talking about. K is your initial amount, so we started with 5 grams. As far as that a value, that growth or decay factor, we're talking about a half-life. So the decay factor is going to be 1/2. Now, the slightly different part comes with that exponent. Typically, we would just put the x up there, but because we're talking about a half-life period of 20 days, we have to take that x and put it over those 20 days. Now, what we're going to do with this is we're going to try to figure out when there's going to be 1 gram remaining. And I'm actually going to use my calculator to help me out. So in my calculator, I've got that function typed in that we just came up with. Now I want to figure out when this is equal to 1. So in my y2, I'm just going to put 1. And I'm going to look for where these two graphs intersect each other. So if I hit graph, there's my two curves. Now I notice that I can't see them intersecting yet, but because this blue graph is coming down, that intersection is going to be happening somewhere off to the right-hand side. So for my window, I'm going to change the x max, and I'm going to go out to 100 and see what that does for me. So if I hit graph, I get this picture. I'm looking for where these two graphs are equal to each other, so where they intersect each other. If I go second trace, option number 5 is intersect. When it asks you for the first curve, mine is on the blue curve, so I'm going to hit enter. It switches to the red graph, or that y2 graph, so I hit enter. So it's going to look for where those two lines intersect. And it looks like it's at an x value of just a little bit less than 46.5. So we could say after 46.44 days, there would be exactly 1 gram left. That's going to be it for this video. Thanks for watching.